Chapter 14, we're going to be talking about electronegativity. This is another of the periodic trends. This is the tendency of an atom to attract electrons when chemically bonded to another element. So we're going to look at two trends. We're going to take a look at the group trend, so that's what happens when you go up and down, so vertical. And we're going to take a look at the periodic trend. That's what happens as you move across a period. So first of all, let's populate some of these atoms that I have drawn here. And some of the scales are not exactly to size, since these are mostly based on freehand. This time, as we go across a row, I'm going to compare beryllium to magnesium. They are both in the alkaline earth metals, so they both have 2 valence electrons. This one has a charge of 12 plus. I'm going to put the 2 electrons in the inner shell, 8 in the second principal energy level, and then 2 valence electrons in the third principal energy level. Okay, let's take a look at what happens. Electronegativity actually decreases as you move down an electron. And here's what happens. Electronegativity is how much an atom wants to attract another electron to itself. So we have an electron that's kind of flying around. The electron can either come over here to beryllium, or the electron can come over here to magnesium. Now, a free electron wants to get as close to the nucleus as it possibly can. So where it can get as close to the nucleus as it possibly can is in beryllium, because there it's going to be in the second principal energy level, whereas if it's going to the third principal energy level, it's going to be farther from the nucleus. So electronegativity decreases as you move down. That's because there is more shielding electrons in the inner principal energy level. This reduces the effective nuclear charge. So this one has a higher electronegativity, and this one has a lower electronegativity. Now, it happens that since both of these are in the alkaline earth metal, they have relatively low electronegativities, but beryllium's is higher than magnesium's. Now, let's take a look down and see what happens with periodic trends. And in this case, we're going to be moving across the second period from lithium all the way over to fluorine. And let's go ahead and put our protons in first. We have 3 protons in lithium's nucleus. We have 2 electrons in the first principal energy level. There's our 1 valence electron. Fluorine, we've got 9 protons in our nucleus. Remember, because we have more protons in the nucleus, that first principal energy level has been pulled towards the nucleus. And the same thing occurs with the valence shell. It is pulled closer to the nucleus. So there we have, oops, I drew an extra electron in there. Let me see if I can erase that baby. Just edge that out. Okay, there it goes. Okay, now we're going to get to neon, which has 10 protons in the nucleus. And I've exaggerated what happens with the principal energy levels here, mostly because I can't draw very well. So neon is actually very much the same size as fluorine. They're almost exactly the same size. There's actually an anomaly here that I don't want to discuss, so we'll show neon as being smaller than fluorine. So in this case, we've got 8 valence electrons. We have 7 valence electrons. We have 1 valence electron. And here's our little electron that is flying around looking for somebody to join. Okay, so it has to be at the second principal energy level, but it's pretty far from the nucleus because there's not a great deal of pull from this 3+ charge. comes over here, and it can get nice and close to the nucleus. So fluorine is going to be more electronegative than lithium because the electron can move into this principal energy level, which is at a lower energy than this one in terms of distance from the nucleus. And then finally, we can go to neon, except there's a small problem here. This second shell is already full. There's no room at the end. There's no space for another electron. So what happens is fluorine is the most electronegative. Because the electron will be closer to the nucleus. This has a very low electronegativity. Compared to fluorine, because an electron is going to be farther from the nucleus. Neon has no electronegativity to speak of, because if you're going to add another electron to neon, what you're going to have to do is you're going to have to add a third shell. And then it's going to be, a new electron would be a great distance from the nucleus, relatively speaking.